Good afternoon. Welcome to lectures 81 and 82 on thermodynamics of materials. Today we will continue with solution thermodynamics. Actually, we will take a number of classes on solution thermodynamics, maybe 7, 8, even 10 to satisfactorily cover this subject, this topic. So today we discussed Raoult's law last class. Today we will start with Henry's law. Henry's law. Note that Henry's law for solute and also another thing, dilute solution. Not only solute but should be dilute solute. So dilute solution. So what is the law? According to Henry, this is that vapor pressure of a species I. Vapor pressure. This is vapor pressure. Vapor pressure I of the species Pi is proportional to xi, the mole fraction of I. Or Pi is k times xi. K is the proportionality constant. K is a constant. Proportionality constant. If you divide by or activity of I, as we know, it is ratio of vapor pressure of the state under study divided by the standard state is what? K by Pi 0 times xi. This is known as gamma I0. Gamma I0 times xi. This is known as activity coefficient of the solute. This is the 0 for what I would say. Actually, it is 0 concentration, but popularly known as activity. This is not standard state. This 0 has nothing to do with standard state. This Pi 0 is standard state or standard state. We have used standard state superscript 0, but this superscript 0 has nothing to do with the standard state. What this 0 means? 0 concentration, dilute solution, so dilute that it tends to 0. Hence this superscript 0. What is this then? Activity coefficient of the species of I, of the solute rather, it is better, right? Of the solute I at infinitely dilute. This is the popular expression or popular phrase, infinitely dilute concentration. This is popular. This is popular. But I give actually an alternative this expression alternative defining of gamma I0, which is activity coefficient of I at zero concentration, at its zero concentration. Zero concentration. There is not much difference between these two, because zero concentration and infinitely dilute concentration means tends to zero. Infinitely dilute means concentration tends to zero. So in a sense same, but I will stick to this at zero concentration. Activity coefficient of I at its zero concentration. Later on I will show you just unnecessary this difficult phrase infinitely dilute concentration. Clear. This is better. Activity coefficient at zero concentration. This zero for this zero. This superscript zero for this zero. Okay. Given this, note this. Note that the Henry's law. Okay, that Henry's law is valid at small concentrations. At a small concentration domain of the solute. In that domain, activity AI is proportional to xi. See, this is a constant. This is a constant. Acha. Note, it is proportional. Note further that gamma I0 is constant in Henry's law domain. That is, gamma I0 is not function of xi in Henry's law domain, in this domain. Alternatively, it can be said that activity xi relationship is linear in Henry's law domain. The straight line. So straight line means the slope of the straight line is constant, this gamma I, and slope is independent of concentration because linear relationship. So these are the comments that we made about Henry's law, and notice this. Okay, this I wanted to show you with note. Distinguish Raoult's law from Henry's law. Raoult's law, see what? AI is xi. Henry's law, there is no deviation from ideality. This is ideal solution. No deviation from ideality. No deviation from ideality. But Henry's law accepts deviation. Accepts. So gamma will be considered. So and it says what? AI is not xi but rather gamma I 0 xi. This law in this law okay in this law describes the deviation from ideality. Ideality, low concentration regime, domain, regime or domain. Now actually it is time to show you that I show you the diagram for Henry's law. Henry's law. So what is Raoult's law? You recall? First of all, the AB, a binary solution I am considering. Unless mentioned otherwise, we will consider binary solution. AB. AB plotted against mole fraction B as 0 to 1. When it is 0, it is pure A. When it is 1, it is pure B. Pure A, pure B. What is Raoult's law? You know, last day, activity is mole fraction. So just very easy. Raoult's law. Raoult's law. This is what? AB is XP. What is Henry's law? Deviation is accepted. Deviation is included. So deviations, suppose we consider negative deviation. So negative deviation, last day I discussed this negative deviation. Okay, let us be more particular about the regime. Sorry. Okay, don't worry. Good enough. Good enough. So Henry's law considers this low concentration of the solute B, and what it says, activity B XB relationship is linear. So say it is non-linear. See, at high concentration non-linear activity B XB with the deviation. This is negative deviation. Okay, so it is linear. So Henry's law is applicable in the linear domain, which is at low concentration of solute. So what is this? So here see, this is a linear. This is Henry's law. If we extend this, this is Henry's law. Why I don't extend up to 1? Because then it will be solvent. High concentration of B, that cannot be. Henry's law for dilute solution. So dilute regime. This is here after this straight line. So you can say this is Henry's law. This is Henry's law domain. What are the features? AB, AB versus XB. What are the given? AB versus, how will you identify AB versus AB XB? Well. AB versus XB linear. That is gamma B, which is gamma B0 is constant. Constant means is not function of composition. It's not function of XP. These are the initial statements about the Henry's law. Now, so we can write this. Okay, anything else here? So Henry's law accepts deviation from Raoult's law, but only describes the activity mole fraction relation for low concentration of the solute, not at high concentration. See, at high concentration deviation is there. So when it is linear, it describes. Later on, I tell you, later on, note this, important. Later on, we'll see that Henry's law is debatable. This I will show you. This will be shown when the regular solution will be discussed, will be taken up. Just give a brief idea. What happens in this regular solution model? It says gamma is a function of composition. Throughout gamma is a function of composition, including the dilute concentration. But it says gamma is a constant. So it will be in conflict with the regular solution. So this part I will resolve. It will be resolved later, okay? And what is to be done, okay? So in that case, okay, we'll consider that how gamma. Yes, we'll consider how to find gamma I0. Suppose there is no, according to regular solution, it continuously changes, continuously becomes non-linear. Finally merges with the Raoult's law, that is different issue. But in the solute, as solute, it continuously, it is non-linear relationship of activity versus XP. That means gamma B is never a constant in this dilute regime or in this in the solute regime. What will happen in that case? What will be gamma B0? No, at infinite dilute there is no linear segment. So the slope of this is gamma B0. The slope of this, okay, this is the linear segment. The slope of this linear relation AB XB, this straight line is the gamma B0. But if there is no linearity, how will you get gamma B0? What is gamma B0? Let me write here. Another way I am talking. Gamma B0 is the slope, the straight line slope of AB XB relation at dilute concentration of solute. So this is the slope because this slope, this is the slope of the AB relation, which is straight line. XB straight line relation, straight line linear relation in the slope of AB XB linear relation at dilute concentrations of solute. So this will be resolved, will be taken up and will be resolved. So particularly when we will consider interaction coefficients and regular solution. So this much, okay, very good. Now we have to, so suppose you see another thing, you note this. So let us follow this full entire curve, full length. What you see, this is Raoult's law. We are not discussing today. We are discussing Henry's law. Suppose first of all you consider this is the factual curve. This is the curve which is shown underneath the Raoult's law. This is the activity XB relationship over the entire region. What you see here, that initially for small concentration, dilute concentration of B, there is a linear behavior. Then it actually breaks into a non-linear behavior. And finally at high concentration of B, as it should, it merges with the Raoult's law. This we said last class. At high concentration, when XB tends to 1, AB tends to 1. So this I said, note, when XB, this I said other day, XB tends to 1, then XB B no longer solute, becomes solvent. When it is 1, means XA is mole that time, so that will be solute. But anyway, when XB tends to 1, then what happens? Gamma B, what I said, gamma B tends to 1. That is AB tends to XB, AB tends to XB. AB tends to XB, that is Raoult's law. That is gamma B is 1. This line, it merges with the Raoult's law. If it takes Raoult's law, the curve merges and it has merged. This is always true. So at the low, Henry's law, at high concentration, Raoult's law. And there it is neither Henry's nor not Raoult's law. So in this is a factual curve. So I can write here, this is the factual curve. Factual curve. So this is actually, so in this we see. Now another thing we may write here, note here, when XB tends to 1, AB tends to XB, Raoult's law. And again write note 1 second also, just here to complete this comparison, when XB tends to, little underneath, when XB tends to 0, 0 means dilute concentration, then what happens? AB is gamma B0 XB. AB is gamma B0 and XB tends to 0, AB is gamma B. This is known as Henry's law. This is Raoult's law. This is Henry's law. When AB is gamma B0 XB, so this is gamma B0 is, I have written somewhere, gamma B0 is value of gamma at 0 concentration. Alright. Gamma B is 1, here gamma B 0 is gamma B 0 concentration of B. Of course, it is non-zero. It is, I'm very sorry, it is not 1. It is not 1. See, clearly see, 1 is here. Raoult's law, gamma b is 1 all along. Here it is not. So it is actually, it will be fraction, less than 1. It is less than 1, as we know, negative deviation gamma I is less than 1, and positive deviation gamma greater than 1. So these are the, now if I superimpose here the another one, suppose this is the AA curve, as you know. So A curve, how will you draw? You know, so again draw the for AA curve, actual curve. Okay, so what is this? Because last day we discussed this. Okay. This is the Raoult's law. Again, you follow AA, and what is the XA? XA is right this side. XA here. XA is, this is B, means XA is 0 here to 1. XA 0 to 1. 1 means pure A. 0 means it is pure B. So A versus XA relationship is actually, this curve is actually to that axis, to this axis, and this is for this scale, AB scale, this is AA scale. Now what is the, then again you will again consider negative deviation. How to draw this? Again, initially a linear part to contrast with another color chalk. So let us see it will work. Or I draw this here. This is Raoult's law, straight line. Okay. Sorry. Initially straight line, then bend and merges with the merging with the Raoult's law, Raoult's line. Deviation here all along. This deviation again here you can write. This is the gamma A0. This will be gamma A0. In the same way, we define gamma B0, the linear part. This is non-linear. Okay. Now, what I interested here to show you, consider when. So you see one interesting observation. You just consider this domain. Okay, this domain. Okay, sorry. This has been sorry. If you consider a vertical line like this, like this, at this concentration, what you see? At this concentration means B is the solute. If XB small means B is the solute, and XA is large, close to 1, tends to 1. When XA tends to 1, okay, so you see the A is merging with the Raoult's law. So A, the solvent, follows Raoult's law in this concentration, at this concentration. So in this concentration domain, in this concentration domain, solute obeys solute B, follow this tail line. Solute Henry's law, solute Henry's law, and solvent red one obeys Raoult's law. So this is the rule. Okay. So the rule is, I'll show you again. Follow this. So okay, I will show you this. Okay. See, this has merged with this. Okay. So Raoult's law. So A has merged with the Raoult's law. So A follows Raoult's law in this concentration. A, the solvent, follows Raoult's law, while the solute follows Henry's law. Or you can say, when solute follows Henry's law, solvent follows Raoult's law. So this is actually an axiom. Okay, so this I can write. Now can I remove this? Here, just write this. So rule when the solute obeys Henry's law, the solvent When solute obeys Henry's law, the solvent obeys Raoult's law. You see clear, okay? See, this side also you can see here. If you consider this domain here, who is the here B is the solvent. B is high concentration, pure B, almost pure B. B, the solvent, follows Raoult's law, and A is the solute now. A follows this tail line behavior is Henry's law. Okay, B. Okay, so when solute obeys Henry's law, the solvent obeys Raoult's law. This proof, thermodynamic proof, will give you. Okay, these are the things that I wanted to initially talk about Henry's law. So proof is this: you start Henry's law. Start with Henry's law. A is the solvent, B is solute. Start. B is solute. When solute obeys Henry's law, that means what is this Henry's law? AB is gamma B0 XP. This is Henry's law. B obeys. Is it okay? Size is okay. You can read this. My handwriting is okay. This writing. Okay. So AB is gamma B0 XB. AB is gamma B0 XP. Start. The Henry's law. I can write here Henry's law or the solute B. Never ever solvent. These are ridiculous. So never up to solve here. See, I have drawn a extension here up to certain, just to show the slope clearly. Nothing else. Here it ends. Henry's law ends. Then gamma B0 is no longer valid. For example, here what is this? Did I write here gamma B0? No longer valid. It becomes gamma B in general. This gamma B activity coefficient is gamma B in general. So what is the gamma B value at high concentration? A merge with Raoult's law means 1. Raoult's law means gamma B is 1, gamma I is 1. And what is here? Henry's law domain, gamma B is gamma B 0. And what is the speciality of gamma B 0? It is constant over the concentration range, small concentration range, the dilute concentration range. Or you may call infinitely dilute concentration range. Henry's law is this. Let us see if we can prove this. Or ln AB, ln gamma B 0 plus ln XB. Can I remove this? Remove this. We don't need anymore this one. This or right, or d ln AB is what? D ln gamma B 0 plus d ln XB. Now can you tell me what is d ln gamma B 0? D, differential of gamma B 0. Gamma B 0 is a constant in the Henry's law domain. So here this is 0 since gamma B 0 is constant, as we have said, is not function of composite. Right here is not function of XB, and this XB is changing. It can change, but the XB changes, but gamma B does not change, remains as gamma B 0 in the Henry's law domain. So this is dl and XB. Call it equation 1. Next, you have to introduce one equation. Okay. Before we will have established it. So this is Gibbs-Duhem equation. This will be established Gibbs-Duhem equation that I have to resort to prove this. Gibbs-Duhem equation is what? This we will study later. Maybe 2-3 two classes or next class or okay, next to next class. Gibbs dual equation is what? To be covered later on. To be covered later on. What is that? XA DGA cell molar free energy DGA. This relationship is the DGB bar is 0. Now we recall this gives DM. Or what is DGI? Remember fugacity. So you always have to connect the previous things. Okay, what you have already understood. DG is RTD ln F, then RTD ln A. So what is this? XA RTD ln F first. DG is BDP minus SDT, then RTD ln F under isothermal condition, then it is RTD ln A. AI, because AI is Fi by Fi0. Recall this. Unnecessarily, I will not go back. Time wastage. RT, DL and AB. If you cancel RT from the two terms, then you have or XA DLNA plus XB DLN AB is 0. Is 0. So right, this is also known as Gibbs-Duhem equation. There are many different forms of Gibbs-Duhem. 4 or 5 forms. Okay, many forms. So this is also Gibbs-Duhem. So another form of Gibbs-Duhem. Another form of Gibbs-Duhem. Another form of Gibbs-Duhem. Another form of Gibbs-Duhem equation. In terms of activity, this is in terms of partial molar free energy. Then in terms of activity coefficient. Then other thermodynamics properties. Or I will call these two. Now remove this part. Remove this part. Then what you will get? We will now combine 1 and 2. Combine 1 and 2. What you will get? So, see what is DLN AB is DLN XP. So from 1 and 2, from 1 and 2, okay, what is this, right? XA DLN A plus XB DLN AB is what? DLN AB is what? DLN XP. DLN XP. Or X is 0, or XA DLN A plus XB D ln XP is what? You know, D log X is what? D ln X is dx by x. So what you write? XP by XP. Now XP cancel, or XA DLN A plus DXP plus DXP is 0 is what? Is minus DXA is 0. Why? Since the XA binary system, 2 mole fraction together is 1. All mole fractions sum to 1. So binary system xa plus xb is 1 or dxa is minus dxb. This is common thing about binary system. xa plus xb is 1, dxa is minus dxb, or xa d ln aa, is dxa. Oh, yes, why? dxb is minus dxa, I have already written here, is dxa, or d ln, sorry, or d ln activity of A is nothing but dxa by xa. Again, dxa by xa is d ln xa. Integrating. Integrating, you have AA ln AA is ln xb plus c. C is the integration constant. Tell me, I'm very sorry. xa, very sorry. ln A xa. Now tell me, now how to get this? Evaluate C, find C by knowing the boundary conditions. What is this? We know the boundary when xa is 1, when xa is 1, what is the xa is 1? Xa, this way, xa is 1, xa is 1, what is the activity? Xa is 1 means, oh, you don't have to, even you don't have to refer to this figure. When x is 1, pure A, and what is the value of A? Pure substance activity is 1. We know this standard state. So when x is 1, A is 1, this gives you, this leads to 1, 1 means C is 0, or this leads to what? ln AA, hence ln AA is ln xa, or AA is xa. This is Raoult's law. This is Raoult's law. We see when solvent B follows Henry's law, solute, I'm very sorry, when solute B obeys Henry's law, solvent can never follow Henry's law. Henry's law for solute. When solute obeys Henry's law, solvent A obeys Raoult's law. It's proved. Raoult's law for A. So it is proved, okay? So this is proved. One thing, okay, we have completed this part. Next we will take up the mixing functions. Today we'll start with mixing. Next is mixing functions. So mixing functions, we will first consider actually the two pure substances are mixed up to form a solution. Let's say pure A and pure B is mixed to form a solution, homogeneous solution. This we have considered, and then we'll see whether this mixing process is a spontaneous process, or what are the different thermodynamic functions that can be found for mixing. Start. Okay, start. Na moles. okay, right here, write this. Na moles of A pure, you can write standard state. Pure means you know Raoult standard state, conventional standard state, in standard state plus Nb moles of B, again pure, and standard state at their standard state. This I may not write, automatically means standard state pure is under constant temperature pressure and the process is mixing. What you will get? Na plus Nb moles, they mixed up and they form a solution, single phase solution or alloy or mixture sometimes, okay, moles of solution. This is if I want to sketch this, I will sketch here, you know, where we have sketched previously the mixing things. Suppose this is the partition. This is partition. This is your Na moles of A. Na moles of A. Right. Na moles A, and this is Nb moles B. Right here, both are pure. They are taken in this system, cylinder piston system, and pressure, as you do often by the cylinder piston arrangement, constant pressure P and constant pressure process as well as constant temperature process. We have often considered this for chemical reactions, and this is constant, this is temperature constant, thermostated temperature. This is the partition. Okay, this is the partition. Now if we want to get them mixed, then we have to slap the partition. So we partition is snapped, partition snapped, partition snapped means like this, okay? Partition is snapped. Then what you will have? Again you can draw same thing. I will draw this constant pressure, again thermostated as before at the temperature of T as before. What do you write here? Na plus Nb moles of no longer pure solution, moles of AB solution. We'll consider just any solution. Later on, we'll restrict this to ideal solution or non-ideal. We'll consider later, but it is generally a solution. So this, okay. So what I write here, what I should write here, some space. You need some space here. So this I say left hand side. I say unmixed state. Like this. This is also unmixed state. Left hand side is this. Right hand side is this. Unmixed state. Call also as state 1. Initial. State 1. This will be what? This will be what? Mixed state. Final state, or say state 2 better. What we want to do? To see the free energy change. Gives free energy change of this process. To find the objective to find the gives free energy change the mixing process This is a start. So I am writing delta G as we are used to 1 to 2. Delta G 1 to 2. Okay. Delta G 1 to 2. 1 state 1 to state 2. I have written here state 1. State 1 is what? As you know, G2 minus G1. This is known as I tell you delta Gm prime. Okay, now it's beginning. This M is the mixing function, mixing properties. The whole life we will use this. Very important thermodynamic function. Okay, we have started free energy of mixing, entropy of mixing, enthalpy of mixing, internal energy of mixing, volume change due to mixing, all we have to consider. Then we will consider another function. This I will take up shortly. Excess function later. So these are all coming. So delta Gm prime is what I should say. You follow me. Let me write first. What is this? G2 minus G1. You are very easy. Follow. This is the 2. This is the 1. So write that side. What is this? Nmoles of A there. Nmoles are present with their. What is the free energy of this state? Free energy of A with nmoles plus free energy of B with Nb moles. So for nmoles for A moles, but this is impure state, solution state. So it is not. It should be given this. Impure state is bar, K bar, plus likewise Nb Gb bar. You remember Gi bar minus Gi0 is RTL and EIL. Number of times we have done. So this is no doubt minus G2 minus G1. G1 is what? Right? Again nmoles, but this time A pure. So and standard state. So Ga we how do we describe this? So, okay, how do you write this? Na Ga0 plus Nb Gb0. Okay, this is the delta G. This is known as this free energy change is known as, since it is a mixing process. So delta G for mixing. Then why this superscript? You remember superscript I taught you when extensive property and intensive property, particularly when you started with heat capacity, total heat capacity, molar heat capacity, all these things, total free energy, molar free energy. So this is total what? Na plus Nb moles involved here. And when molar involved, when Na plus Nb is 1, like molar heat capacity for 1 mole. So similarly here, this is actually, what is the name then? Integral, as different from partial. I will take up soon here. Integral total because extensive property, total molar. No, I am very sorry. Integral total. I am very sorry. Free energy of mixing. Integral means effect of the two both of A and B together. What is this then? Here a little bit of juggling or arrangement. Na bar minus Na 0, group them together, Ga plus Nb Gb bar minus Gb0, group them together. What is this? Na common, Ga bar minus Ga0 plus NB times GB bar minus GB. Oh, what I have done? Oh, here, why is this NB GB bar? Write this fully since I am writing NB GB bar minus NB GB 0. You bracket NB common GB bar minus GB 0. What is this known as? Na is easy. GA bar discussed later previously. It is again mixing pure impure. GA bar minus G 0 is GA bar mixing, M for mixing. GA bar minus G 0 plus NB GB bar minus GB 0 is GB bar M. If you ask me what is this? GA bar M is partial molar free energy of integral. This is partial molar energy of M for mixing. The mixing A in the mixed state GA bar pure GA 0. Energy of mixing partial molar free energy of mixing for A, and this is similarly GB bar is what? GB bar is what? GB bar similarly partial molar free energy of mixing similarly mixing of for B. For A or of A, right? Of A of B. So this is again see compare for 1 mole and N moles are involved. So Na GA bar M. And partial, why? Anytime partial means impure. Partial means impure. So impure in the solution state. Okay, impure means part. Okay, so GA bar partial means that is another one B. Okay, partial molar like partial pressure. When partial pressure means when there are more than one component. So more than one component. Partial molar free energy of mixing of B. So this and this is in contrast is integral because integrated together. Total free energy of mixing of it. So this we got. Now this is right here. Nice, right? Extensive property. Extensive property. Why? Why extensive? For since extensive property. For Na plus Nb moles, not 1 mole. When 1 mole, it is intensive property. For Na plus Nb moles. Now we will be interested to find for 1 mole. So dividing. So now dividing both sides. This is for Na plus Nb. So for 1 mole, dividing both sides by Na plus Nb. What you get this side, right? Or delta Gm prime by Na plus Nb. Right hand side, Na by Na plus Nb. Ga bar M plus Nb by Na plus Nb. Gb bar M. Now this is known as, tell me, this is known as what? XA, mole fraction of it. Mole fraction of it. Mole fraction of A. And likewise, this will be XB. And what is this? Okay, what is this? Shall I write here? Is XA. This is better write at the same line. Okay, and next line. Or what is this? Extensive. This is what property? Divide away for 1 mole. So this is for 1 mole right here. So what's the name? Integral, again integral, because together integral. Tell me, integral, what will change? Free energy of mixing again, but no longer total. Not for total Na plus Nb moles. Na plus Nb moles. But for 1 mole, 1 means Na plus Nb is 1. So for 1 mole, when Na plus Nb is 1, this we have to divide this. So integral total is off now. Integral molar for 1 mole. Okay, right. Integral molar free energy of mixing. Okay, that is for 1 mole. No longer for Na plus Nb moles, for 1 mole. 1 mole means that is Na plus Nb is 1. So what you get, then you write here, what is the name of this? Oh, sorry. What is symbol? Symbol is what? Symbol is what? It cannot be primed anymore. What it will be? Just delta Gn. Intensive property. Intensive. Intensive property. Right here. Intensive property for 1 mole. See, extensive for Na plus Nb, intensive for 1 mole. Na plus Nb is 1. So this much is okay. Also you write here, wasting this side. So delta Gn now, unprimed. Achha, recall its capacity. How do you write this? 2 ways I told you. Cp and Cp prime. Cp is the molar heat capacity. This prime is the unprimed. Prime is total heat capacity. Also similarly G prime. Molar free energy, total free energy. This is actually Cp prime. Molar heat capacity means 1 mole substance. Then 1 mole iron heat capacity. This is 4 moles iron, 5 moles iron. Similarly this. Okay, because this is 1 mole free energy, 1 mole iron free energy, 4 moles iron free energy. This we discussed, so unnecessary. Now no more discussion. So delta Gm is right nicely. What you got? Xa. Sorry, I'm very sorry. Xa Ga bar m plus Xb Gb bar m. Box this, very important, and you can do yours very easy. This is what is the name? Integral molar free energy of mixing. So integral molar for 1 mole. So that's why means Xa moles. Here, see what is the difference between this and this? Yeah, right. This and this. What is the difference? It's similar. Here Xa, here they are Na, because it is Na plus Nb moles. And so Na plus Nb. Here 1 mole. Na plus Nb, that means Xa mole, Xb mole. Xa moles of A, Xb moles of A. So similarly, Na will be replaced by Xa. Xa is the mole fraction. So Xa moles of A plus Xb moles of B means if you sum this, Xa plus Xb is 1. So for 1 mole. So this is actually the. So this is so anytime see no difference. It has. So in this case, if see Ga. Shall I? It's better I give here a box also. Sorry. See, no, Ga bar m in both cases, Gb bar m. Ga bar m and Gb bar m will retain both cases. So when it is integral molar integral total, integral molar Xa will show up, mole fraction will show up, and when it is total, so Na plus Nb. This is moles, Xa, but it is less than 1. Xa moles plus and Xb mole, that together is 1. So this is for 1 mole, this is for, okay, this Na plus Nb mole. So this part is clear. Next, let us proceed this. Okay, so delta Gm, shall I write? Shall I remove some places? It is better I write here. Can I write here? This side a little bit. This side will be comfortable for me. Just now onwards from this point. From this point. Okay. Divide this. Don't have write this. From this point, you consider. So what we have got? Let us write this nicely. Okay. Start from this point. Delta Gm is XA GA bar M. I'm writing this. Okay. I'm writing once more. XA GA bar M plus quickly XB GB bar M. Sorry. GB bar M. What is GA bar M? Tell me. GA bar M is GA bar minus GA0. Is what? GA bar minus GA0 is what? A moment ago I have shown this. GA bar minus GA0 is what? G is RT DLN F. There. GA bar minus GA0 is RT DLN A. RT DLN F. DLN fugacity. Then since it is D is there, it will be fugacity is actually activity is fugacity by fugacity standard state. So Fi is, so it is actually RTDLNA because Fi0 is a constant. So this is a number of times we have used. Gi bar M, no, Gi bar M is what? Gi bar minus Gi0. Gi bar minus Gi0 plus XP RTLN no, I've made a mistake. RTLN AB. Well, this D is okay. Gi bar M is recall. Gi bar minus Gi0, which is known as Gi bar M, is R. To DLNAI. I'm writing here. RTDLNF is Fi is RTDLNAI. Recall AI is Fi by Fi0 and Fi0 is a constant, so you'll get this. So RTDLN or DLNA. I'm very sorry. DLNAB. So this is the expression for, no, there is a mistake there. Acha. Delta GM is XA bar M. Delta GM so wait a bit, let me check this. XA GA bar minus GA0 plus XP GA bar M. Oh, sorry. No, I made a mistake here. What is this? Recall DG is VDP minus SDT under constant temperature out is VDP is RTDLNF or integrate GI bar pure to impure GI bar minus GI0 RT, this will be outside, RT are out. Oh, I'm very sorry. Is Fi by Fi0. This is known as RTLN AI. So what mistake I made this? So RTLN right correctly. Yes. This is known as GI by M. So start here. So RT ln, I'm very sorry, activity of A plus XP RT ln activity of B, tidy up, RT common, what you are getting, XA ln A plus XB ln AB. This is, remember, delta GM. You may again box in this form, important. This is valid for any solution. We have not mentioned what type of solution, any solution, what type, ideal or positive deviation or negative deviation, no. So for valid for any solution, ideal. Now we will actually make a special case for ideal solution, because ideal solution is a reference and also simple. So when the solution case okay, when the solution is ideal, when the solution is ideal, solution is ideal, then what will happen here to this expression delta GM? Delta GM you can write, or you can write additionally delta GM ideal. Don't have to, because you are writing here, don't have to, otherwise you can write. Is what change you will get, you will make here, what change you will make? RT you cannot change, XA no, ln A, activity of A is what according to ideal solution? Mole fraction, and activity of B is mole fraction. So that simplification will write delta GM is RT XA ln XA plus XB ln XB. Happy? Delta GM. Okay. This is under constant. Remember this thing under constant pressure and temperature. I have not mentioned, but all along we are doing under constant pressure. We are doing all these derivations and all this, writing this expression under constant temperature and pressure. Okay. This is right somewhere delta GM under constant pressure. Remember this is also delta G. We are used to considering delta G of the process. It's an initial, final. G2 minus G1, delta G of the process, delta G of the system, process or change in energy of the system. So this is still there. Still we are considering the system. This equation, we have given a name that energy of mixing integral or total or integral molar. But this all the same, the energy change of the system as it moves from this state to that state. What is the energy change of the system? Delta G. That delta G we have number of times used previously in chemical reactions and all other things. Okay, even with ideal gas, we actually use okay, properties of gases, okay, behavior of gases. So delta G is there from state 1 to state 2. This delta G is a special type of delta G here. What is the name? Since it is a mixing process, delta GM. So delta G is delta. This is the delta G is delta GM. Prime, unprime, we have explained. So very good. RT, XL and XP. This is the. So I will start from this point, go, and I will remove all. This is under constant pressure, temperature. So it is only I will actually maintain since this is unmixed state. It is better I retain the figure. Objective is what? To find the energy of change. What is the objective? The objective is answer. This is this, and if you write only, this will be only, okay, here XA will be replaced, XA will be replaced by NA and XB will be replaced by NB. Okay, so I write this. Okay, good. Okay. Okay, very good, very good, very good. Start from this point. Delta GM. Start from this point. Star. delta Gm ideal solutions. We write, since we are considering ideal solution, we are considering only ideal solution. For ideal solution, what is the result? Delta Gm wait a bit. Let me write this. Delta Gm is RT XA ln XA plus XB ln XB. Now, if you consider this, okay, very good. Delta Gm, it is actually right for ideal solution. Delta Gm. This is also our famous delta G. This is also delta G. No change. We have not changed anything. The same principle we are using, delta G of the system, delta G system, right? Delta G system, no problem. Delta G for the process, no problem. The system. So that is again further G2 minus G1, etc. G2 minus G1. Of course, this is for Na and B. It will be XA XB. Okay, G2 minus delta G system. Also you write. Further you write. Okay, delta Gm. This is also, or you write. This is also delta Gm PT. You further define this, specify the constant, this process under constant pressure temperature. Partition snapped, constant pressure, constant temperature, I have written here. Okay. So what happens? This is now one thing before I start. Actually, let us see. Delta Gm positive, negative, or zero. Ideal solution. Okay, good reference. See here, can you tell me whether it is positive, negative, or zero? See, positive, negative, or zero. See, La is less than 1. Mole fraction is always less than 1. So negative. So this is a delta Gm is negative only. What delta Gm PT or delta G PT, delta Gm, or right in your language, previous language, delta G PT, delta G prime PT, does not matter, is negative. What does it mean? This is a spontaneous process. This implies mixing is a spontaneous process. Mixing is a spontaneous process. So, this we have actually established. You might say, sir, this is for ideal solution. For non-ideal solutions, real solutions, what would happen? What is the difference in real solution? This is Na and this is Nb. This is ln XA and ln XB will be there because these are written Ga bar M. See, if you follow this previous lines, okay, this is A, this is AB. A is XA. I'm very sorry. I'm very sorry. What is this? Right. What I'm trying to tell you. Okay, this is XA and AA. By the way, it will be AA and AB, but AA is also activity for impure substance. The solution, in solution, activity will be pure substance 1, and others are always less than 1. This we consider. Activity will be less than 1, again negative. This is for 1 mole. For Na plus Nb mole, Na plus Nb into negative, again negative. So mixing is a spontaneous process. This is proved. I gave you examples for spontaneous process. 3 examples I gave you. One is heat flow from high temperature to low temperature is a spontaneous process. Then another I said mixing is a spontaneous process. Then I said chemical reactions are spontaneous process. Those who occur are spontaneously occur. These things I said, and this is different from spontaneous is different from irreversible. Okay, this I am not going back, but this remember this is a spontaneous process. Very good. anything else, but you may see what is the delta G. I have written there. Good, good. G2 minus G1. G2 minus G1. See, recall, little bit confusion I want to remove. Little bit. What is the criterion of spontaneity? Irreversibility. What is the criterion? Recall. I'm sketching you here. Then I will remove this. Let me remove this. I'll show you. Recall. I gave you two criterion in terms of gives free energy, and I asked you to be alert about it, careful about it. I'm showing you chemical reaction. Recall. I say recall. Previous discussion. Previous discussions. Discussions for chemical equilibrium, spontaneity, and impossibility. Recall those classes. This will be not out of place. Follow this. Suppose simple reaction A plus 2B goes to 3C. This reaction under constant temperature pressure. Recall. This I am showing you. This was the figure. Okay. Yeah, right. Say. So add criterion spontaneity. I am writing here. Follow this. Criterion of spontaneity. Criterion of this criterion. What is this criteria? Criterion or criteria? Tell me. First is DS universe. Original. Second law statement. DS universe greater than equal to 0 or less than 0. Okay. Recall this. This is for spontaneity. This is for equilibrium or reversibility. This leads to dg prime pt less than equal to 0 or dgpt or simply or dgpt also you can write. Okay. dgpt. But if you write this, okay, this gives you, okay, right here, this is for spontaneity, this is equilibrium, from which you get, remember this NMOs dg prime, this I want to go back to this class, dg prime by dn, this is very effective. Rather than this will be effective. This I will explain. Dg prime by dn is this is nothing but delta G. Delta G less than 0 equals to 0. And greater than 0 is greater than, right somewhere. Greater than 0, here actually less than 0. Less than 0 is impossibility. In entropy, less than 0 is impossibility, and here greater than 0 is impossibility. Just you accommodated everything, all the possibilities, three possibilities. So dg less than, this is actually dg prime by dn is, this is known as delta G. Suppose at this state, your question, so what is placed here? G prime, and under constant temperature pressure, remember here actually you have getting NC moles or like this, or N, so called N. Recall this. Here what is your whether is at this reaction is spontaneous, what will be your answer? What is the criterion? Sir, delta G less than 0 or this slope less than deep. So you see, recall this. Slope is, this was your answer. Slope is negative. So reaction is spontaneous. What is the what is happening here? This slope is means delta G is 0. So delta G. I am very sorry. Slope is negative. Slope negative. Delta G less than 0. This is also, this is delta G. This is actually delta G. So reaction spontaneous, yes, delta G less than 0 and the slope is negative. It follows this, satisfies this condition. Reaction spontaneous means if we take this composition of A, B and C, at this composition, now delta G is what here? It is not G product minus, I am very sorry, it is not final state minus initial state. Two states are not there. This I clarified. This is single state. Interesting. With single state with this state is this state and certain moles of A and B and C all are there at a temperature pressure. Whether the reaction will occur on question is raised and answer is this: if delta G less than 0 or at this state reaction will occur. But what is not this state minus that state, not final minus only one, not final minus initial. It is only one state while there are no two states. But how is the delta here? G of, because this is G of product sigma minus G of reactant. So this way it is a difference at this state. At this state C and the free energy of the reactant is A and B together. So this is delta not to at a given state. At the given state. No change of state. No change of state is referred to here. But this is one thing. But we are used to considering state 1 to state 2. That is also there. Delta G, one state to, so this state to this state, or this state to this state. So this will be what? Then this, suppose we actually start from this. I give you another problem here. So this is one way of using. Okay, that's delta at a given state. Now you want to as a change of state. As a change of state is what? Which one? As a change of state, I would say tell you is what? Delta G PT. Okay, is what I tell you. Also delta G is this is right. If you say, sir, delta G, recall. So this is the initial state, and this is the right start. A B. What is the delta? Yeah, system is state A. Final state. So what is this delta G is what? Tell me, delta G TP, delta G prime or delta G TP is what? Delta G TP is what? Here negative. So system will spontaneously move from this state to this state because this energy so can be considered. You consider the delta G TP and right this way GTP state, sorry, minus GTP state 1, then you can get a delta involvement. We always consider state 1 to internal energy, enthalpy energy, entropy, state 1 to state 2. So if you want to this means this is actually GTP of state 2 means state B, and this is state A. State 1 means state A. What is this value? Clearly negative. So it is spontaneous. So it is spontaneous. This is one when two states. But here this I said. Be careful to use this. Why? I am showing you. I am showing from state 1 to next state 1. This one B prime state. If we again cautious about using this delta GTP. It's actually how this is coming from this actually. DG prime TT. This is actually from this delta GPT less than 0. But where you how delta GTP how apply? Follow this. If you want to apply in the same manner A to B prime, again negative. This is less, but this is although negative right here, negative written. Yeah, spontaneous. Is negative. Previously it was spontaneous. sorry, it is spontaneous, I am very sorry, is spontaneous. As we clearly see, yeah, reaction will move, spontaneous, and will stop. This is equilibrium state. Minimum is delta G is 0. So don't worry, don't take up this. Here negative, but this is not. Why? Because the reaction will occur moving down. This point stops at equilibrium. Equilibrium point. I will not get equilibrium to B prime. So delta TP, for that matter, delta G prime TP, okay, risky, or you have to alert about which two, between two states. Which two states you are considering? That means you have to consider a beyond, before equilibrium, before or after equilibrium, before and okay, including equilibrium state. So this, so domain for this, these two equilibrium point, this domain, this is active on. So it will be tricked then. It will you run into errors. Okay. So this is the story. Now in this light, if you say what we are doing here, in this case, what we are doing. So it should be confined to the final state must precede equilibrium state, or maybe may lie on the equilibrium state. What is this? So this is the initial state, this is the final state. Is there what is the equilibrium state here? What is the equilibrium state here? It is not unlike chemical reaction. Middle. Here constant. Here the minima. But here what is the equilibrium? Equilibrium means what? The reactant and product both will be there. Reactant some concentration of, so that they will make up the equilibrium state. Right? What is this? It is fully converged. This is the equilibrium state. Then this is the equilibrium state. The full conversion, not stop. That means when equilibrium means here equilibrium. If the equilibrium constant is infinity, then what? The equilibrium constant is infinity. What it will be? The minima. Constant infinity unlikely means very large value, or say then minima will be here, means full conversion. A plus to 3C. If it is finite, it will be stopped in the middle with A, B unreacted and C produced. But we are fully, see, this has happened here. So right, then any value, the delta T PT can operate without any difficulty anywhere, any concentration here, because it is always, it's the equilibrium states, or say on this state to this state to this state, we can apply this, okay, or it is on the equilibrium state, no problem. So we have used this delta GTP because I actually asked you to be cautious about that, and now I myself using delta GTP. Yes, this is our previous discussed. This is over. So delta GTP, I have written here, that is negative. I am using myself because I know this criteria. Because this is not a chemical reaction, because it doesn't stop in the middle. So it has gone fullest extent, full conversion. Now nothing left behind. Solution. So you can apply. Recall two criterion of spontaneous equilibrium and impossibility. Delta GTP one, another is just delta G at a given state. Question is about given state reaction will occur or not. Here, but here at that state, combined minus free energy of reactant combined. So this is the result. Or here to step 2, that is actually about. Traditionally we use delta H2 minus in ideal gas. A number of times we have considered this energy change, enthalpy change from state 1 to state 2. okay, system moves from state 1 to state 2. So if you delta G from state 1 to state 2 you want to use this caution, but this time there is actually that caution is actually doesn't hinder us, okay, because it has actually satisfied the caution. It has actually complied with the okay, this with the requirement, that is this is actually the it is initial state and equilibrium state. Initial state and equilibrium state apply anywhere. So thank you very much. This actually one mental problem or mental okay, confusion actually I wanted to remove, but now move on fast or go to this quickly, very quickly. So this one thing we have got now, that this is a spontaneous in a different way soon, very soon. But before other function, mixing function not only gives me the entropy, right, one by one. SM, you understand what is this? Delta SM is the, this is what's the name? Tell me. Similarly, name it. Tell me. Integral. Since it is not prime actually, for integral molar. What is the name there? Integral molar free energy of mixing. So what you write here? Integral molar entropy of mixing. Now, if you have followed this, then you can very easily move on and confidently. Delta SM. Now, what is the from delta GM? Common instruction there. Common is what? When delta GM is a function of temperature given, then entropy is minus. Never ever forget this. Delta GM, derivative of temperature with respect to temperature under constant pressure composition. Never ever forget this. dg is VdP minus, somewhere I write dg is, never forget this, you always, so this minus. Now do this here is what you are getting. I am writing here minus dt. So there are one, okay, minus ddt of this, these are temperature independent, so minus r ddt of t is 1 minus r xa ln xa plus xb ln xb over. So this box, this, so one by one you keep on boxing. This free energy part over, this entropy part over. Now just curiosity, this again if you the process for system and like 1 to 2 minus. So previously it was negative, what it is? It is see ln xa again, mole fraction is less than 1, log negative, so there is a negative here, positive. Delta is mixing. Now incidentally recall this was discussed and arrived at when what we did, when we are talking about when we are learning statistical thermodynamics, statistical interpretation of entropy. Exactly the same result. This actually I computed that it will classically also, that is, this is statistically, classically the same result. So same result. What is this kind of which way we discuss that? As configurational entropy change. So this entropy change is fully recall is configurational entropy change, and I have to distinguish thermal entropy change from configurational. This was considered in the statistical thermodynamics as a configurational entropy change process, entropy change. Okay, configurational, but number of ways A's are arranged and B's are arranged, okay, and number of ways A and B switchovers are considered. This is discussed fully. Configurational entropy change as different from thermal entropy change. Very good. So all reconciled. Okay, this what else? What else needed? Okay, this is positive. I will take up this positive. Okay, soon. Important. Before this, I finish other things. Where is delta Gm, delta Sm? There is delta Hm. Delta Hm is what? Tell me. Delta Hm is delta Gm plus delta G is H minus Ts. Tsm. This is actually right nicely. Delta Hm. T is the constant plus T. T is the constant temperature. T delta Sm. Now what is this value? Oh, delta Gm. What is this value? If you do this, to see this is what? What? Tell me. RTXA, copy, RTXA ln XA plus XB ln XB, and T delta S is minus RT, the same. Minus RT the same. XA ln XA. What is this? 0. All right. That is delta Hm is 0. So this is very important observation. Now no enthalpy of mixing. So that's why ideal solution, I told you, this positive deviation and negative deviation can be related to the enthalpy of mixing, partial or integral or total. So, and for ideal solution there is no deviation and there is no actually no deviation, and so there is no enthalpy factor as seen here. Okay, but this will be positive for the real solution, positive deviation, and negative for real solution with negative deviation. Okay, so this is note. What is Q? Q is, recall, Q is delta Hm under what condition? Q is the heat interaction. You are interested to find the heat interaction. Enthalpy change is required, but heat interaction sometimes can be related to enthalpy change, sometimes internal energy change. Quickly, so is under constant pressure. And recall, Q is delta H under constant pressure and no non-mechanical work. So this question is not there. No non-mechanical work under constant pressure, which you have all along consider. So Q is delta H, and which is, that is 0. There is no heat interaction. That means no. That what? That means what? That is no heat is transferred from the system transferred from the system to surrounding. No heat is transferred from the system to, nor no heat admitted from the surrounding to the system. So no heat interaction, no heat exchange. That means if we mix these two solutions, will there be any heat effect? If it were exothermic, warmer, hotter, or heat will be transferred to the thermostat if it is exothermic. If it is endothermic, heat will move. I'm sorry, if it is exothermic, heat will be transferred from system to surrounding. If it is endothermic, then what will happen? Heat will be transferred from system to surrounding. It will be colder. Okay, so heat will be transferred from this, means it will be colder. Endothermic reaction. Exothermic reaction, it will be hotter. It will be, so this is the difference. But in this case, no heat effect. So these are three important: delta Gm, delta Sm, delta Hm is over. Next is a delta thermodynamic under constant pressure is Q. We are not satisfied with delta Hm, fully satisfied. Q is actually the heat interaction, and that is equal to the present condition. For example, Q is not delta Hm under constant volume. No, internal energy change will be. So this is very important. So we found that under this condition, Q is also zero, so no heat interaction. He neither enters into the system or leaves the system. This is one three. Then before this, let me compare. Shall I? I think I can remove this. This I can remove now. This I can remove. This not remove. Now quickly take up from this point. Delta Hm. What else left? Tell me. What else? You like whatever you like. Delta Vn. Delta Vn means what is this? Tell me. Then volume change. So again you write integral molar volume change on mixing. What is the delta Vn equal? What is Vg is Vdp minus Vt. I wrote somewhere. Here again is how to get V. How to get V from Vg? See, tell me del G by del P at, tell me at del G by del P V, then del V will be the same way. Del G D del G D del G. Achha, first you write V is what? Del G del P. So delta V will be D delta G del P. Delta G M. D delta G Dg dP at constant temperature, and of course composition of diffusion. Same composition, I would say, same thing we are doing. What is this? We are changing the pressure. Pressure P1, P1, P2, P3, other things remaining constant. Temperature and composition means Na and Nb. Say 3, 4. Without changing these 3, 4 moles and changing the temperature, pressure is changing. Then what is the, how the free energy will be affected? Then this derivative will give this. But in this case, what it is? What is, let us see, under constant temperature, what is the delta Gm? Take a look. Take a look. Shall I write this? Shall I? Do I have to write? Write. If it helps you, write this. Write this. I'm writing. See. Del P, delta Gm, you write truly. RT, XA, ln XA, plus XB, ln XB. Maybe third. This is square bracket. This under constant temperature composition. What happens inside is what? Temperature is a constant, and these are all constant. So compositions. So DdP is what? So in volume change also, just simply volume change on mixing. It is a big name. Volume change on mixing is 0. No volume change. That means if this state is 3 cc, 4 cc, 7 cc, this volume will be, final volume will be 7 cc. No volume change. No enthalpy change, no volume change. Okay. Any expansion or contraction due to the process. This is the, remember, I'm very sorry, ideal solution properties we are discussing. Next is what? Ideal solution, continued. Shall I write in here? Ideal solution continued, right? Acha. Ideal solution property continued. Ideal solution property continued, so that you understand that we are discussing this. Only ideal solution. When you wrote activities, mole fraction, then ideal solution actually was. consider. Otherwise, activity remain activity coefficient time mole fraction. Don't worry this part. So 0. Last is what? Delta V H G S H V U. Delta UM, internal energy of mixing. Internal energy of mixing is what? How you get? You have a easy way. Delta HM plus H is U plus PV. Recall from this delta HM minus delta PVM. Happy is what? Delta HM. P should be outside constant. P delta VM. And you know this value is 0. This value is 0 a moment ago is 0. So this is another observation. I'm going to box this. So delta UM is 0. Still another box. So it will number of 1, 2, 3, and delta VM is 0. So I should write here or write here. Gives a box so that a box here. So 1, 2, 3, 4, 5. What is this? What is the name of this? Delta EM, same way name. Integral molar. What? Internal energy. Internal energy of mixing. That's right. Simply internal energy change due to mixing. What is this? No change. Suppose this is 3 joule internal energy left hand side, pure 3 joule and 4 joule. Total is 7 joule. And what is the internal energy of this? 7 joule. So no change. This is the significance or meaning of this, simple meaning of this. So these part are over. Okay. So next actually I will show you. I do not know whether I should continue because I will give you actually some phase diagram. I will sketch you some phase diagram consistent with this ideal solution and positive deviation from ideality and negative deviation from, and showing positive deviation from ideality and showing negative deviation from ideality. Maybe today maybe actually may not be okay, may not have enough time. So let me check how much. Wait a bit. Papu, hello. So friends, actually these phase diagrams actually will actually be, start next class. We will consider phase diagrams and which are consistent with this properties of the solution, like ideal solution or positive deviation, negative deviation, and consistent with this solution nature, solution property, how the phase diagrams will look like and how they will change also. This part I will take up okay, at the beginning of next class, and then I shall consider excess functions. Okay, these are our plan. So today actually it is better, call it a day, and thank you very much for your cooperation and patience, and thank you all. So see you next class. Bye.